We're talking Taylor and Maclaurin series today. The goal is to express certain functions as power series. And so what do you need to remember? A power series is a series of the form sum n equals 0 to infinity of some sequence involving n's, right? The formula for the nth term just involves n, it doesn't involve x, times x minus a to the n. This is a power series centered at a. So the big theorem, you guys, is if a function f has a power series centered at a, then, well, we can write that function like this. Now, so this is the power series, right? What I'm about to tell you is what the c sub n equal. Guaranteed, if that power series exists. So f of x would equal the sum from n equals 0 to infinity of the nth derivative evaluated at a divided by n factorial times x minus a to the n power. So this is essentially saying that c sub n is equal to, okay, this notation, this looks like an exponent of n, that means the nth derivative. This is basically saying that c sub n is equal to the nth derivative evaluated at a divided by n factorial if the power series exists. So let's write this out longhand so that you get a feel. It's often going to be convenient to write it out longhand, and you'll get a feel for how easy it is to remember this formula. What we're saying then is that the first term in the power series is just f evaluated at a if we agree that when n equals 0, f with the 0 superscript a is just f of a. So when n equals 0, think about it, you plug in 0 down here, you get 0 factorial, which is 1, and then x minus a to the 0 is 1. So you just get f of a for the first term. And then writing it out longhand, next you plug in n equals 1, which means you're taking the first derivative, we'll call it f prime here, evaluated at a, divided by 1 factorial, that's just 1, times x minus a to the 1 power. That would be the second term. And then plug in n equals 2, you'd get okay, if you plug in 2 up here, that means the second derivative, and I'll stick with the prime notation for now, but I'll change it when it gets to be too many of them. So that means second derivative evaluated at a divided by, okay, n for the third term, since n is starting at 0, n is 2, so that means divided by 2 factorial. It was 1 factorial over here, but I just didn't bother writing that. And of course 2 factorial is just 2. Times x minus a to the n, which is just 2, so x minus a squared. Now you get a feel for it. What's the third term going to be? Okay, I'll just, you can use 3 primes, but I'll use just the 3. So that means the third derivative of f evaluated at a. 3 factorial, right? Times quantity x minus a to the third power, and then so on and so forth. This is where we agree that f to the 0th derivative evaluated at a is just f of a. So yeah, and that's a notational item, just like 0 factorial. We agree that that's 1 because it makes our formula work, and same thing here. We agree that f superscript 0 means just the function itself, f. And then it makes the shorthand notation work, otherwise it wouldn't work. Okay, note number 1, the above series is called the Taylor series for f of x centered at a. If a equals 0, the series is called the Maclaurin series for f. And then, very important, the theorem says that c sub n, I mean, if you think about it, the generic power series we developed last time was sum n equals 0 to infinity, c sub n, x minus a to the n, right? This theorem then is saying c sub n is the nth derivative evaluated at a divided by n factorial. Okay, let's prove it. f of x, write it out longhand. What is this formula say f of x is if you write it out longhand? The first term is c sub 0 plus, what's the next term? C sub 1 times x minus a plus c sub 2 times, well, there you go, plus, you could do this the rest of your life. If you ever go to prison, just do this. They'll let you out on an insanity. Okay, C4 x minus a to the 4th power. Let's go to 5, I guess. C5 x minus a to the 5th. Agreed? That's what the power series, the original power definition of power series looks like longhand. Yeah? Let's take derivatives. Oh, fine. Plus dot, dot, dot. Okay. So the first derivative, what would f prime be? What happens to c naught? C sub 0? 0, so you'd get c1, right? For this first guy, you take the derivative of c1 times the quantity x minus a, it's just going to be c1. Because, well, depending on how you look at it, if you wanted to really see it, you could distribute the c1. You take the derivative of c1x, that's c1. Take the derivative of minus c1a, that's 0. But you don't have to do that distribution to see it. OK, what's the next term? Bring down the 2. 2c2 x minus a to the 1 power, right? OK, let's go through this fast. What's the next one? 3c3 x minus a squared, right? Plus 4c4 x minus a cubed. Now, I'm starting to daydream, so if I make a mistake, let me know. X minus a to the 4th. Does that all look right to you? Plus dot, dot, dot. Yeah, this is like watching grass grow. But we got to do it to prove the theorem. OK. Well, the only thing that's really going to be of interest are the first terms. What's going to be left when we take the derivative of the derivative? What's f double prime? Just 2c2. Sounds like do-si-do, right? And then plus what?
6.
Right, but if we want to see a pattern, let's write it as 2 times 3 out in front, or 3 times 2, I guess. C3 x minus a to the 1 power plus what? 4 times 3, c4 x minus a squared plus 5 times 4, c5 x minus a cubed plus dot, dot, dot. I know, very exciting. We'll just do only 3 more. The third derivative, OK, what's the first guy going to be? So this guy goes to 0, right? So just 3 times 2 times c3. We're developing a pattern, in case you're wondering. And then take the derivative of this next term. What do you get? 4 times 3 times 2, c4 x minus a. And then take the derivative of this guy. What do you get? 5 times 4 times 3, c5 x minus a squared. We'll just do one more. I'll bet you'll be able to see it after we do one more, if you haven't seen it already. Fourth derivative. Fourth derivative, evaluated at x, what do we get? So this guy's gone, right? 3 times 2 times c3 is a constant gone, and we're left with 4 times 3 times 2 times just c4. And then what's left plus 5 times 4 times 3 times 2, c5, x minus a. Did I miss anything? I knew I forgot something. Plus 2, or times 2, I mean. So I didn't bring the 2 down. Let me, although it's not going to affect you seeing the pattern, let me get it right. So times 2 right there. OK. Now, let's examine this last one. evaluated at A. So what would the fourth derivative evaluated at A be? Well, what's going to happen to every term after the first term since you're evaluating at A? Every term after the first term has a factor of x minus a to some power in it, right? So you throw in x equals a, you get a minus a, that gives you a zero factor, so the whole term zeroes out, which means every term zeroes out after the first one. So you get the fourth derivative evaluated at a is equal to 4 times 3 times 2 times C4, right? So what do you notice about 4 times 3 times 2? How could you write it using a notation we've been using a lot? 4 factorial. So 4 factorial times C4. So the fourth derivative at evaluated at A is 4 factorial times C4, or C4 is the fourth derivative evaluated at A divided by 4 factorial. But this pattern is going to extend to the nth derivative. So the nth derivative evaluated at A is going to be n factorial times Cn, right? And if you don't believe me, just take a few more derivatives. It's great fun. Convince yourself, and then solve for Cn, C sub n, and you get the nth derivative at A evaluated at A divided by n factorial, and that's it, which is what we wanted to prove, which is the result we were looking for.